Hello, let's continue on the properties of materials. So now we have the idea that there is piezoelectric, pyroelectric, and ferroelectric materials. But what are they? Let's look into more details in this lecture. When any materials undergoes polarization, its ions and electronic clouds are displaced, causing the development of mechanical strain in the material. This effect is seen in all material when it is subjected to an electric field, and this is known as electrostruction. We have piezoelectric, pyroelectric, and ferroelectric materials. So materials that develop voltage upon the application of stress and develop strain when an electric field is applied is known as piezoelectric materials. The ability of a material to spontaneously polarize and produce voltage due to changes in temperature is known as pyroelectric material, and a material that shows spontaneous and reversible polarization is a ferroelectric material. This is a piezoelectric material. So piezoelectric is a phenomenon when there is energy transformation from mechanical to electrical or from electrical to mechanical energy. Figure A shows the direct piezoelectric effect, while figure B is the converse piezoelectric effect. Can you see? When we apply force to the material, it will generate voltage or the electrical energy and save this in the material. Or we can also apply electrical direct current here, and this causes the changes in shape of the material or the mechanical strain. This is piezoelectric materials. This table shows the piezoelectric coefficient D and G for selected materials. So we have quartz, barium titanate, PZT, and so on. And each of these materials have their own D and G coefficient. You don't need to know the values for them, but what you need to know, each material have their own piezoelectric coefficients, and therefore they have different applications. So how are piezoelectric ceramic made? A traditional piezoceramic is perovskite crystal consisting of small tetravalent metal ion, usually titanium or zirconium, in a lattice of larger divalent metal ions, usually lead or barium and oxygen ions. So this is the piezoelectric ceramic at above Curie point or Curie temperature. So they are in cubic lattice. But under conditions that confer tetragonal or orthorhombic symmetry on the crystal, each crystal has a dipole moment. And this condition is achieved when the temperature is below Curie point. Above a critical temperature, the Curie point, each perovskite crystal exhibits a simple cubic symmetry with no dipole moment. But at temperature below the Curie point, the crystal become tetragonal or orthorhombic symmetry and have a dipole moment. Adjoining dipoles from regions of local alignment called domains. The alignment gives a net dipole moment to the domain and thus causes the net polarization. The direction of polarization among neighboring domains is random. However, so the ceramic element has no overall polarization. The domains in ceramic elements can be aligned by exposing the elements to strong direct current, usually at a temperature slightly below the Curie temperature. This is known as polarizing or Pauling treatment. Through this polarizing or Pauling treatment, domains mostly align near to the electric field expand, and at the expanse of domains that are not aligned with the field, and the element lengthens in the direction of the field. When the electric field is removed, most of the dipoles are remain or lock into the configuration of near alignment. the element now has a permanent polarization. As you can see in this figure, this is when the domains is randomly oriented because there is no polarization. Then when we apply the direct electric field, the domains are aligned according to the polarization. And when we remove electric field, the domains remain or unlock and align to the polarization, but with a little tilt. But mostly they are aligned. Or you can also draw a simple diagram like this to illustrate the polarization of piezoelectric materials. So this is random. Domains are in random orientation. Then when we apply electric field, it is aligned. And when we remove, some of the domains will be tilted off, but most of the domains are still aligned or locked in the direction of the electric field. Thus, the opposite phases normal to polar axis develop electric charge when pressure is applied along the axis. The direction of this electric field is reversed when the pressure is replaced by a tension. So piezoelectricity is only observed in crystals which have polar axis, and this polar direction can only exist in point groups, which is non-central symmetric, and there are 21 point groups in this group. Piezoelectric effect is reversible. If an electric field is applied in the direction of polar axis of quartz plate, for instance, the crystal will undergo compression effect of expansion. The application of alternating field will cause the crystal to vibrate, and crystal with piezoelectricity or piezoelectric materials such as tourmaline, ZnS, and PZT. PZT is inorganic material. It is lead, zirconium, and titanate with chemical formula of PbZrX Ti1-X O3. It is a well-known piezoelectric materials. So at temperature above Curie temperature, it exists as cubic, but when the temperature drops below the Curie temperature, it can exist as tetragonal or orthorhombic. So this is the general formula for PZT, PbZrX Ti1-X O3. So X is the substitution dopant amount of substitution. Okay, so X can be between 0 to 1. For instance, we have PbZr 0.52, Ti 0.48, O3, and at this state, it exists as cubic. But when X becomes 0, that means there is no Zr. So it exists as PbTiO3. And for this composition, it has been reported that it exists as tetragonal. But when X equals to 1, that means there is no Ti. The composition becomes PbZrO3. And for this composition, it forms orthorhombic. So we can see that crystal structure actually can change with the substitution of X value or the Curie temperature. Then we have pyroelectricity. When a crystal, such as tourmaline, is heated, the polar ends of the crystal develop electric charges. Heating causes the positive end of the C-axis become positive charge relative to the negative end, and cooling had a permanent electric dipole. The charge that builds up is then dissipated by conduction into surroundings. Changes in temperature change the size of electric dipole. Dipole moment is a vector, that means it has magnitude and direction. So pyroelectricity only arises when the point group has no symmetry operation which alter the direction of this dipole. The dipole moment vector lies in the rotation axis. The condition for the presence of dipole moment are also found in the point group of mirror and 1 for every direction, and the knowledge of symmetry gives us only qualitative indication of the possible presence of pyroelectricity. It does not indicate size of dipole moment or direction of the positive and negative ends. Next, we have barium titanate, or the chemical composition is BaTiO3. The dielectric constant of ferroelectric reaches a maximum near a temperature known as Curie temperature. At this temperature, the crystal structure acquires a center of symmetry, and thus it is no longer piezoelectric. Even at this high temperature, however, the dielectric constant of ferroelectrics remains high. Barium titanate exhibits this behavior, and this is the reason why barium titanate has been used as single or multi-layer capacitors. In this state, vibration and shocks do not generate spurious voltage due to piezoelectric effect. Since the Curie transition occurs at high temperature, so the use of additive or dopants in barium titanate could help to shift the Curie transition temperature to lower temperature. So we can add additives such as strontium, which has been widely studied in barium titanate. Additive can also be used to broaden the Curie transition temperature. For instance, here we have different polymorph of barium titanate and accompanying changes in the crystal structure from cubic to tetragonal to orthorhombic and to rhombohedral. The transition from cubic to tetragonal and from orthorhombic to rhombohedral occur far away from the normal working temperature, but the transition from tetragonal to orthorhombic occur close to the working temperature. So you need to know the temperature and also the changes in crystal structure and know how to draw them for barium titanate. So as we said, barium titanate, BaTiO3. So Ba is actually the A side and Ti is the B side. So we can actually substitute the A side with Pb2 plus or Ca2 plus, and this will lower the transition temperature and also control the piezoelectric properties around 0 degrees C. This is important for underwater detection and echo sounding applications. Or else we can alter the B side by substituting Zn2 plus zinc or stannum Sn2 plus, or known as tin. This will rise both tetragonal orthorhombic and orthorhombic rhombohedral transition temperature. These are the typical hysteresis loop for single crystal, the one on your left, and this is the hysteresis loop for polycrystal. And most of the crystals exhibit polycrystal hysteresis loop. Then we have effect of grain size on permittivity of barium titanate. You can see different size have different permittivity, and the smaller the size, the higher the relative permittivity of barium titanate. And finally, the dielectric constant of barium titanate can be altered by changing the amount of substitution. For example, we can dope or we can introduce additives such as strontium into barium titanate structure. So the structure now become BaX SR1 minus X PiO3. And the X value here actually represent the amount of strontium added into the structure of barium titanate. And you can see the changes in dielectric constant as we increase the amount of strontium into barium titanate. Alright, so that's all for now. We will take a short break and continue in the next lecture with the next properties of materials. By looking at this short video, can you guess what is the material?